So in the previous lecture, we did example 10, which was an example of a hypothesis test on a proportion, and it was a right-tailed test. So now in this lecture, I'm going to do example 11, and it's going to be another hypothesis test on a proportion, except now I'm going to cover a right-tailed test. I'm sorry, a left-tailed test. So let's look at example 11. Let me make this a little bit bigger. It says an e-commerce research company claims that 60% of graduate students have bought merchandise online. A consumer group is suspicious of the claim and thinks that the proportion is lower than 60%. A random sample of 80 graduate students shows that only 22 students have ever done so, meaning purchased merchandise online. Is there enough evidence to show that the true proportion is lower than 60%? Test that alpha equals 10%. So I'm asking you to conduct a hypothesis test on the proportion, right? That's the parameter that we're testing in this case. So we're investigating a population of graduate students, and we're interested in the proportion that have bought merchandise online. And an e-commerce research company claims or states that 60% have done so. So the belief is that the proportion of students that have bought merchandise online is equal to 0.60. But a consumer group comes along and has a suspicion and thinks that the proportion is lower than 60%. So that's actually going to be our alternative hypothesis, right? The suspicion is always the alternative. So let's formulate our hypotheses. That's always the first step. So the null hypothesis in this case is the assumption that the population proportion of graduate students that have bought merchandise online is equal to 0.60. The alternative is what we're testing. So the suspicion is that the population proportion is lower or less than 0.60. So if you want to make a note that this is a left-tailed test, go ahead. And I'm asking you to test at an alpha level of 10%, and as a decimal, that's 0.10. So we're going to state that as well in the first step. So now we know what we're testing. So now we have to take some information. So in this case, we sampled 80 students, and 22 of them have purchased merchandise online. So let's summarize the information that we got from our sample. So let's model the sampling distribution of the proportion. So first, tell me the sample size. So we took a sample of n equals 80 students, and x equals 22 of them said, yes, we've bought merchandise online. So let's formulate our sample proportion of students that have bought merchandise online. So let's get p hat. So remember, p hat is equal to x over n. So in this case, it's going to be 22 over 80. So I want you guys to plug that in your calculator. So 22 divided by 80 is 0.275. So now let's look at our model here. So we have a normal distribution. We can make this picture a little bit bigger. So mu sub p hat's going to go in the center, and we're assuming p is equal to 0.60, right? Unless we could prove otherwise, and mu sub p hat is equal to p, so that's 0.60. And sigma sub p hat is going to be sigma divided by the square root of n. Sorry, I'm like not paying attention. So sigma sub p hat is equal to the square root of p times 1 minus p over n. Sorry about that. So let's plug in. So we're going to take the square root of p, which is 0.60. We're going to multiply that by 1 minus 0.60, and we're going to divide by n, which is 80. And let's go 4 places. So I want you guys to plug this in also. I'm getting 0.0548 for my standard error. So now we're ready to see, relatively speaking, where our p hat lives within this normal distribution. So 0.275 is less than the mean of 0.60, so we're going to put it to the left. So let's say here's p hat is equal to 0.275. How many standard deviations below the mean is that, right? So get your test statistic. So let's calculate z. So we're going to take p hat minus mu sub p hat divided by sigma sub p hat. So we're going to take 0.275 minus 0.60, and we're going to divide that by 0.0548. And we're going to get a negative value, right? Because it's below the mean. So let's take 0.275 minus 0.60, and we're dividing that by 0.0548. And we get negative 5.93. So my z-score is equal to negative 5.93. And let's label that on the curve as well. So this p hat of 0.275 corresponds to a z-score of negative 5.93. So that's pretty far away from the mean, right? Relatively speaking, that's way more than 3 standard deviations below the mean, even though the picture's not to scale. So let's figure out what this p-value is. And since this is a left-tailed test, the p-value is the area to the left of the test statistic. So that green area that I just shaded. And since this is a normal distribution, we could use normal CDF to get this area. And we're coming in from the left, so my lower bound is going to be negative E99, and I'll just use my z-score of negative 5.93 for the upper bound. So let's go to the calculator. So normal CDF, so second and then the VARS key, option 2, normal CDF. My lower bound is negative E99. And we said we'll use the z-score for the upper bound. So that's going to be negative 5.93. So negative 5.93. And since that's the z-score, the mean is 0, the standard deviation is 1. And we could hit enter, paste it, and then enter again. Now, I'm happy this happens because you're going to see this every once in a while, but you have to pay close attention. That p-value is not 1.51. Look all the way to the right. You see how it's 1.51984 e negative 9? That's scientific notation. And I'm going to review what that is. Let me just write this down. So 1.51984 e to the negative 9. So let's talk about this. Because remember, a p-value is just a probability, and a probability is always between 0 and 1 inclusive. It can't be bigger than 1. So 1.51 doesn't make sense. So let me review scientific notation. So 1.51984 e to the negative 9. So this is like 1.51984 times 10 to the negative 9th power. This is base 10. So there's too many zeros in this decimal number to fit on the screen, and that's why the calculator uses scientific notation. So this is like multiplying 10 to the negative 9th power, which is a really, 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 really tiny small number. So the trick is, whatever the exponent is, if it's negative, you're going to move the decimal to the left that many places. So 9 places. So if I move this decimal back 9 places, I'm going to get 0.00000001519884. That's the p-value, which is a really, 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 really tiny number, right? We typically round the p-value 4 places. If we round 4 places, this is approximately 0. So that's the trick anytime your calculator gives you scientific notation. So my p-value in this case is so tiny. It's approximately 0. So fill in 0 for your p-value. And that's as tiny as we could get, right? So I'm thinking, okay, when I compare it to my significance level, alpha, it's definitely going to be smaller. So our decision rule is always to reject the null hypothesis if our p-value is less than alpha and 0 is less than alpha, right? Which in this case is 0.10. So we do reject the null hypothesis, right? So since the p-value is less than alpha, we reject the null hypothesis. So we have enough evidence to go with the alternative. And the alternative in this case is that the dropout rate is lower than 60%. I'm sorry, we're not talking about dropout rates. We are talking about the proportion of students that bought merchandise online. My head is still thinking of the one that we did last time. So P, the population proportion of graduate students that have bought merchandise online, is lower than 60%. So let's write that down. So we can conclude that there is enough evidence to conclude that the proportion of grad students that bought merchandise, we'll just call it merch, online is less than 60%, right? Because that was the alternative, that P is less than 0.60. So there is enough evidence to conclude that the proportion of grad students that bought merchandise online is less than 60%. So this completes another hypothesis test on proportions. We'll do one more in the next lecture. And that one will be an example of a two-tailed test. So notice I did one of each. For means, I did left-tailed, right-tailed, two-tailed. Now for proportions, I did a left-tailed and a right-tailed, and now we'll do a two-tailed.